given a function y is equal to f of x, we can take its derivative, and then we would write dy dx is equal to f prime of x. So the derivative itself is a function. It's a perfectly good function. We saw an example where f of x was 3x squared plus 4x plus 7, and then f prime of x was equal to 6x plus 4. So the derivative itself is in its own right a function. It's a perfectly good function. So you might ask the question, well, what happens if I take the derivative of the derivative? That's something called the second derivative. So the second derivative. So the second derivative is just the derivative of the derivative. So if I were to differentiate your derivative function, you get the second derivative of f. So the second derivative of a function f is simply the derivative, or the first derivative, of f prime. So the second derivative of the original function f is just the derivative of f prime, is the derivative of the derivative. And to denote this, we say d squared y over dx squared, or f double prime of x. So in the Lagrange notation, we just add a prime. So instead of f prime, it's f double prime. And that's the second derivative of the function f. And then in the Leibniz notation, we would say d squared y over dx squared. And then if you have a higher derivative, a third derivative, it's d cubed y over dx cubed is equal to f triple prime of x, and so forth. So this is the notation for higher derivatives. Right. So in this example, I'm not going to compute it using the limit definition, but we saw a similar example anyway, but the derivative of this, if you actually compute it, is just 6. So f double prime of x is equal to 6. So the units of the derivative. So let's look at the units of the second derivative. So we have the units of y. It's supposed to be y. We have the units of x. So y is equal to f of x. We said that the units of f prime, or the units of the derivative, are simply the units of y divided by the units of x. Now for the derivative, we have dy dx is equal to f prime of x. So it makes sense that the units of the derivative are the units of y or the units of x, because it's a change of y over a change of x. But when you take another derivative, the independent variable is still x. So going from y is equal to f of x, the units of the output here were just the units of y. When we took the derivative, we're dividing by the units of the input. So analogously, if we look at this, when we take the second derivative, so when we compute d squared y dx squared, again, we start with the units of dy dx and divide it by the units of the input, which are the units of x. So the units of f double prime will be the units of y divided by the units of x squared. So let's say f of x is your loudness in decibels at a distance at x meters. So then f prime of x will be decibels per meter, and then f double prime of x will represent decibels per meter squared. So the second derivative, you can think of that as, for if you say f double prime at 80, I'm just going to make something completely up, is 2, that would mean that if you're 80 meters away from the engine or the source of the sound, 2, so if you increase your distance by an additional meter, the rate of change would increase by 2 decibels per meter. So by adding 1 meter to your distance, the rate of change is changing by 2 decibels per meter. So this would be how much the rate of change changes by when you increase your distance by 1 additional meter. So it's the units of the derivative divided by the units of the independent variable x. So let's look at another example with physics. So we had said that x of t was the position of a particle at time t, and then position and the time have units, but maybe meters and seconds, or maybe miles and hours, but there's a number of different units you can use for this. X prime of t was the velocity, so it's meters per second. So the units of x double prime of t should be the units of the derivative and then divided by the units of the independent variable t. So it's meters per second, which we say meters per second squared. So meters per second, and we divide all that by seconds. It's meters per second times 1 over second. We say meters per second squared. And so the second derivative is what we call the acceleration, right? So for example, in free fall, if you have drop a brick and it falls, we say that gravitational acceleration is 9.8 meters per second squared. What that means is that every second, and it's actually a constant acceleration, so we can say that each second the velocity increases by 9.8 meters per second, right? So you start off at rest, 1 second later in your free fall, you'll be traveling at 9.8 meters per second. 2 seconds later, you'll be traveling at 19.6 meters per second. So each second, 9.8 meters per second is added to the velocity. So that is the second derivative.